So now we're going to get into a discussion of how the electrons are arranged in the atom. And to do that, we're going to look at the distribution of electrons among the orbitals for the first 18 elements. So, to determine these structures, we have to use some guidelines. So I'm just going to go through them right now. The first of which we have talked about before, the fact that for each orbital they can occupy, or they can be occupied by a maximum of 2 electrons. All right, so that's the first guideline. No orbital can have more than 2 electrons in it, and of course the electrons must be spinning in opposite directions if they are both occupying the same orbital. Electrons will go into the lowest energy orbital available, right? And they will enter a higher energy orbital only after the lower orbitals are filled. We're going to see that in the examples later on. The third guideline is that for atoms beyond hydrogen, the orbital energies varies, as you can see here. The s orbital will have a lower energy than the p, will have a lower energy than the d, will have a lower energy than the f. All right? So that's within any particular shell where these orbitals exist. That would be the order of the orbitals within that shell. Okay. So what you see here are situations where the electrons are occupying your s orbital firstly, and then the next energy orbital will be the 2s orbital. You're going to have the 2 electrons occupying those as well. And then when you have a sublevel which has more than 1 orbital, then basically when you're assigning the electrons will go into the orbital singly, as you can see here, right? And you'll notice when they are assigned singly, they are spinning in the same direction. And then if you have any more electrons, they will be assigned like this. All right, so in other words, you add each electron singly to each orbital, and then if you have any more electrons to add, you add them to each orbital until they're completely filled. All right. Okay, so as far as the nuclear makeup is concerned, we can determine the number of electrons based on, or the number of protons in the nucleus based on the number of electrons. So for example, in the case of fluorine, we have a total of 9 electrons. In the neutral atom, that means that you'll have 9 protons in the nucleus. In the case of sodium, you have a total of 11 electrons. You're going to have 11 protons in the nucleus, and so on and so forth. Now, let us talk about the electron configuration. This is basically a shorthand way of showing you how the electrons are distributed. And very often you're going to see a symbolism like what you see here on the screen. For example, 2p6, I should say. What you should understand is what this symbol means, right? So 2 represents the principal energy level, or the shell. P represents the type of orbital, which comes from the particular subshell. And then 6 here represents the actual number of electrons within the set of p orbitals, right? So this is what you're going to see a lot in describing how the electrons are distributed among the orbitals. So now we're going to get into the exercise of how the electrons are assigned. All right, so what we're going to do is use boxes to represent the orbitals. And we're going to use the arrows to represent the electrons spinning in one direction or another. All right, so that's what these arrows represent. So each direction shows the possible direction of spin for the electrons. So the first electrons will go into, for the hydrogen atom, the lowest energy level, which is the n equal 1, and it has the 1s sublevel, and there's only one 1s orbital within that sublevel. So the first electron will go into it, and that would be basically it, how the electrons are arranged in hydrogen. And we can represent it in a shorthand way using this symbolism: 1s1. 1 indicate that the s orbital is from the first shell, s indicate the type of orbital, and this one here, written as a superscript, represents the number of electrons in that 1s sublevel. The next element in line is helium, which has 2 electrons. We can get to the electronic configuration of helium from hydrogen by simply adding 1 electron to the electron configuration of hydrogen, and then and then that would be it. And we can write the electron configuration as 1s2. And of course, the 2 electrons occupying the same orbital must be spinning in opposite directions. So this is the electron configuration of helium. All right. The next element in line is lithium. So to get from lithium, or to get to lithium from helium, we take the electronic configuration of helium, and because this sublevel is completely full, that means that the next electron added will go into the next higher energy orbital, which would be the 2s orbital, and that would be the electronic configuration of lithium, or you can represent it as 1s2, 2s1, and then the next element is beryllium, and in that case, this would be the electron configuration. You're going to have 2 electrons occupying the 2s orbital spinning in opposite directions, and therefore the electron configuration will be 1s2, 2s2. The next element in line is boron. So to get boron, we have to add 1 electron to the electron configuration of beryllium. So this is the electron configuration of beryllium. This 2s orbital is completely full, so therefore the next electron will occupy one of these 3 2p orbitals. It doesn't matter which electron or which orbital will get the electron. So we place the electron there, and that would be the electron configuration of boron. The next element will be carbon. Or, by the way, this is the SPDF notation for the carbon or the boron atom. The next element would be carbon. So to get from boron to carbon, this is boron. The next electron will go into one of the other 2p orbitals, like that. And therefore, the electron configuration will be 1s2, 2s2, 2p2. And then when you get to nitrogen, this is the same as carbon. So the next electron will go into the remaining vacant p orbital, and therefore the electron configuration will be 1s2, 2s2, 2p3. All right? And then from there, the next element is going to be oxygen. So this is what nitrogen looks like. This is the electron configuration of nitrogen. To get from nitrogen to oxygen, we have to add an electron, and that electron can go into any one of these p orbitals. So therefore, we put 1 electron there. Of course, the electron that is added must be spinning in the opposite direction to the electron that is there before. So therefore, the electron configuration for oxygen would be 1s2, 2s2, 2p4. And then from there to fluorine, so this is oxygen. This is the electron configuration of oxygen. To get to the electron configuration to fluorine, we just simply add 1 electron to any one of these 2p orbitals. Again, the electron added must be spinning in the opposite direction to the electron that was there before, and therefore the electron configuration is 1s2, 2s2, 2p5. And then we get to neon. So this is fluorine. What you see here is the electron configuration of fluorine. So the next electron will be added to this 2p orbital, and that would be the electron configuration of fluorine. All right. Okay, then the next element is sodium. So this here, what you see here so far, is the electron configuration of neon. So to get from neon to sodium, we have to add an electron to the next higher energy orbital, which would be the 3s orbital. So that is sodium, and that's the electron configuration of sodium. And then for magnesium, to get from sodium to magnesium, we simply add an electron to the 3s orbital, spinning in the opposite direction, and therefore the electron configuration of magnesium is what you see here, and so on and so forth. So basically, you should be able to pick up on the pattern of how we assign electrons. We simply assign electrons to vacant orbitals. We spread them out among orbitals of equal energy to get the electron configuration of the particular element where you have orbitals of equal energy. What you see on the screen here is what happens after magnesium. You have aluminum, silicon, and the same pattern is what you follow. You just simply add an electron to where you can add it to get the full number of electrons, and this shows you basically the electron distribution for everything up to argon, which is the 18th element. All right. And that's basically it for this video. So what we're going to do for the next video is look at how the electron arrangements, how that tells something about the position of the element within the periodic table. All right. Until next time.